This is a presentation about weather and how weather transfers energy in the atmosphere from one place to another through storms. So we're going to be seeing how storms are actually energy movers. So our first map here is a typical synoptic weather map. We see the United States and all the station models over here. Here are a couple that are telling us information about important weather variables in those locations. We have an isobar map. Here, those blue lines are showing us lines connecting points of equal pressure. And we're going to be looking at two areas over here. One area that is under high pressure and one area over here under low pressure. So our question is the wind speed in the area near the highs greater or faster than the area here near the lows? So we're going to be using isobar spacing to piece that together. And going to this area near the highs, we can see how the isobars are much farther apart over here. So we have a bigger spacing apart over here compared to our area here in the lows where the lines are really close together. So therefore our pressure gradient over here is much lower. There's a much less difference in pressure over this area than over this area. And therefore the wind speed is much faster here. The greater the pressure gradient, the faster the wind speed. Now we're going to look at another map of the United States at the same time, and we can see the movement of air here, and we can see that we have a low over here around Michigan and Canada, and we have a high over here in southern Texas. What important concepts about air movement around highs and lows is this map showing? So you can see over here in the high we have this motion of air, and around the low we have this kind of motion of air. And what you should know at this point is air rushes out of a high. You can see it's even rushing into the low. It's curved by the Coriolis effect, of course, but it also goes clockwise out of the high. It rushes into the low in a counterclockwise pattern, and these are distinctive of these types of pressure systems. The next part, you're just going to have to take a few notes on some important weather concepts, and I'd like you to label each line in your worksheet with the weather phenomenon or weather factor it's showing. So number one is what we just talked about. Air rushes from high to low pressure. Number two, at a low pressure area, the air is rising. Number three, rising air expands, cools to the dew point, and then condenses to form clouds. That's why low pressure is our lousy or stormy weather. Now, once that condensation creates water droplets big enough, they will fall as precipitation. And then cooler air that is denser is going to sink and create a high pressure area. And this is our clear skies, because when air sinks it warms above the dew point and skies clear up. Now in this map here we're seeing radar, and the radar is actually the colored area over here showing that there's clouds and rain or some form of precipitation over here. And the question is, well, where did this energy come from? What process creates clouds and is going to produce then rain or snow or whatever kind of precipitation is happening at that moment? and it's a process that releases 20 to 60 joules per gram. And you should know that process as condensation. So condensation releases energy in the atmosphere. Now the next part, we're going to be looking at an area where the air is rising and creating stormy conditions, and an area where the air is sinking and the skies are clear. So our first is the high pressure area, and I'd like you to figure out what the air temperature is, the dew point, and the pressure at the station in Texas using these numbers here. And is the relative humidity high or low, and what's the percent cloud cover? And you can see here that the air temperature is 43 degrees Fahrenheit. The dew point is 22 degrees Fahrenheit, and our air pressure is 1019.4 millibars. And we have no cloud cover here. We have clear skies, is what we'd expect in a high pressure area, and that's because the air temperature at 43 degrees Fahrenheit is much higher than the dew point at 22 degrees Fahrenheit. So these numbers are far apart, meaning low relative humidity and clear skies. Now we're going to go to the low, where the air is rising and we have our storm. And you're going to answer the same questions about this. And here we have a situation where the air temperature and the dew point are equal. So our relative humidity is high, and not only is it high, it's going to be 100% when they're the same. But our air temperature is 44, our dew point temperature is 44 degrees Fahrenheit. Our air pressure is 999.6 millibars. And our percent cloud cover is 100%, as we'd expect for 100% relative humidity. Now our front is a boundary, and it's a boundary between colder and warmer air masses. So we're going to take a look at a cold front here, and we're going to look at both sides of the cold front. So we have one area over here which is in front of the cold front, meaning the cold front hasn't reached it yet, and we're in our warmer maritime tropical air. And then we have a station in back of the cold front, meaning the cold air has covered it, and we're in our continental polar air. So the question is, how is the air behind the cold front different from the air in front of the cold front where the cold air hasn't reached yet? And you're going to be comparing the temperature, the dew point temperature, the wind direction, and speed over here. And what we can see over here is that in our station model that is in front of the cold front, the air temperature is a lot higher. So it's warmer, as we'd expect in tropical air. Our dew point temperature is also much higher than the air here, which is what we'd expect in maritime air that formed over the ocean. In our continental polar air, instead, we have much colder air and much moister air. Now we're going to take a look at the precipitation relative to this cold front, and we can see that the precipitation is in a narrow band near the cold front. So when cold air plows into warm air, it rises. The warm air gets forced up very quickly and produces a very intense band of precipitation that is short in length. Now for comparison, if we look at a warm front, when warm air collides with cold air, the warm air just gradually glides up the cold air and actually produces a large band of precipitation. So warm front weather is a longer period of rain or snow than cold front weather. Now let's take a look at both sides of this warm front. So we have air in back of the warm front here, meaning that the warm air has reached this area, and we have air in front of the warm front, meaning the warm air hasn't reached it yet. And here's a station model here that may be a little hard to read. This is a 35, a 34, and a 046 over here. This is 58, 47, and 113. Now what we can see is behind the warm front. This again is the leading edge of the warm air. So all the warm air in back of it is here. And the air is warmer, 58 degrees Fahrenheit instead of 35 degrees Fahrenheit in the colder air in front of the front. The air is more full of moisture. We have a higher dew point at 47 degrees Fahrenheit than 34. Sorry, that one got away. And the other thing is that the wind direction is different on both sides of the front. Here, the wind direction is from the northwest, and here it is from the southeast. So when a front passes, we get a significant change in wind direction. The other thing is relative humidity. Behind the warm front, the storm is past, and the relative humidity is lower because the temperature and the dew point are much farther apart. When we're right near the warm front, this is where the storm is, and the air temperature and the dew point are close together, and we're getting precipitation here. Now onto the fact that fronts do actually move, and they follow the typical storm track in our latitudes. So we're going to look at a place before and after a front passes over it. So here's a station model in Canada, and here's the cold front. So the front hasn't quite passed over it, and this cold air hasn't quite passed over it yet either. So the air temperature is 28 degrees and the dew point is 28 degrees Fahrenheit, and our pressure is 1009.6 millibars. Now the front is passing over this area, and we can see that it's gotten frigid here now. So now the air temperature is 1 degree Fahrenheit, and the dew point is really low, meaning really dry air is 0 degrees Fahrenheit, and the pressure has gone up to 1022.1 millibars. So when cold fronts pass, the cold air in back of it changes the weather in that area that it's passing over. So now we're going to see the general track of these fronts. We're also going to see what happens in the terms of the energy transfer. So here in the Gulf of Mexico, water is evaporating from here into this empty air mass, and evaporation absorbs energy. And for every gram of water that evaporates, 2260 joules are absorbed. Now later, this front, this warm front, has moved this direction from here to here, and the water vapor that evaporated here condensed here, releasing that energy, releasing the 2260 joules per gram of water. So energy that was once here now has been brought to here. And now we're going to watch and see the typical direction of these fronts here. So our question is, what compass direction did these fronts and the accompanying storms move? Now, just like fronts, air masses move. The front, remember, is just the beginning of that air mass. So we're going to watch an air mass move south. And what we have here is a map of the United States with isotherms. So here we have temperature lines. All places along this line are 40 degrees Fahrenheit, whereas here it's 50. And we can see that down here the colors change as we go from cold to warm and hot. So we're going to see this big mass of cold air creep over the United States and bring the cold temperatures with it. And we can see that the United States is getting colder and colder as time goes on, and changing from the warm air to the cold air. So we're going to be asking or answering what type of air mass we would have just seen move south. What two-letter code is it? And what is its source region, meaning what geographic location did it come from? The other thing is what type of air mass is down here in our warm air. What two-letter code would that be, and what geographic region is it from? And that ends our presentation on fronts and air masses, and we wanted to see how things in our atmosphere actually move. The atmosphere is in a constant state of motion, and that's what changes our weather from one pattern to the next.